Okay. All right. So where were we before the crash? Oh, sources are represented as phasors, inductors and capacitors and impedances. So phasor. Again, phasor is a vector, is a rotating vector in the complex plane in the frequency domain. It's a representation of the time varying signal. Okay, so here below is the time varying signal. It's simply illustrated on its side. Okay, so it's just rotated. Here's the x-axis. As always, x-axis is time. Okay, x-axis is time. And as we know, that AC sinusoidal waveform has a different value at any given point in time. So a phasor is simply a snapshot, a single snapshot of a single moment in time. And then moment in time is when it crosses the x-axis. Right here. Okay. It's simply the moment in time it crosses the x-axis. Right there. And that's what a phasor is. The value of a phasor is, because it's a vector, simply needs length and direction, magnitude and direction. So it's the length of the vector and the phase difference or phase shift of the waveform gives you the phase angle for that vector. Okay, phase angle for that vector. That vector is rotating at the vector is rotating at a speed of omega radians per second, but it is not needed to describe the vector. The vector needs only two things: magnitude and phase angle. That's it. And those are directly obtained from the time domain expression right here. If v of t is Vm cos of omega t plus theta, then the magnitude is Vm, phase angle is theta. And that is the reason why we do not describe theta in radians. We do not want to combine it with omega because we need that phase angle to describe that vector. Any questions? Does that make sense? Right? We need that phase difference to describe that vector. Note that omega is not part of the description of that phasor. It's not part of the description of the phasor. Again, it's a rotating vector. One full circle is 360 degrees. So if you have a time domain expression, this one time period, which is one full cycle, is equal to 360 degrees or 2 pi. This is a positive half cycle, negative half cycle. So one half cycle is 180 degrees or just pi. Right? Concepts that every engineer would be familiar with, mathematically speaking, at least. And so to do a phasor transform, all you would need to do is, let's say, for instance, V of t was Vm sine omega t plus or minus theta. You would use the identity sine x is equal to cos of x minus 90 to subtract 90 degrees and translate it into a cosine function. Minus 90 degrees. Sine x is equal to cos of x minus 90. Okay, the reason we do that, of course, there is a derivation. There's a phasor transform derivation. But again, it forms a right angle triangle. It forms a right angle triangle, sorry, this way. And that's where it comes from. So if the expression is not in sine, you must convert it into cosine to write the phasor. Once you have it in cosine, you simply take the magnitude and the phase angle, and you directly write the phasor for that source. Okay? Directly write the phasor for that source. The source could be voltage, V of t. It could be current, I of t. Doesn't really matter. Okay? You can write the phasor form directly. It's simply a complex number. Again, remember, we are doing this transformation to complex numbers so that we can reduce the analysis down to simple circuit analysis problems. Okay, circuit analysis problems. All right, any questions? Any questions so far? We good? Okay. And let's look at the complex representation for the components. We introduce the term known as impedance. Impedance is a complex quantity represented again using complex numbers. It has an imaginary component as well as a real component. Impedance is the sum of resistance and reactance. Z equals R plus X. Impedance is represented by uppercase Z, resistance with R, and a new term called reactance with X. Okay, reactance with X. All three are synonyms of each other. Impedance comes from impede, resistance comes from resist, reactance, well, reactance is due to the reaction or the response that is elicited due to an applied input or voltage current. An applied input, whether it is voltage or current. Okay, and they're all synonyms of each other. Again, impedance, resistance, and reactance are kind of all synonyms of each other, but technically, impedance is the sum of resistance and reactance. Okay, resistance and reactance. So, what is reactance? Reactance has a basis, has a physical basis in real life. It has to do with energy storage. Okay. Let's say, for example, you apply an input current to an inductor. That input current to an inductor gives rise to a magnetic field, which stores the energy that is being received from that current. It gives rise to a voltage, right? When current enters the inductor, you have voltage with a polarity of plus at the point of entry. The magnetic field and the energy stored in that magnetic field gives rise to an opposing voltage that has opposite polarity to that inductor voltage. Now, when you try to change the current that is flowing through that inductor, that magnetic field is going to oppose any change in that value. Remember, if it's constant, inductor behaves like a short circuit. If you try to change that current, it's going to oppose any change in that current. That opposition is reactance. So again, reactance is opposition to any change in the input voltage or the input current. It's similar to a capacitor, where a capacitor, once it acquires all the voltage, behaves like an open circuit. But if you change that voltage, it is now going to have current flowing back in the circuit. So again, reactance for an inductor, reactance for a capacitor opposes any change in that input quantity. Mathematically, we represent it using the imaginary number. So this is important, okay? There's a distinction. Complex numbers, we have a real component and an imaginary component. For an impedance, which is a complex quantity, the real component is the resistance R, and the imaginary component is the reactance X. So you may hear or you may read the words, or you may come across the words imaginary reactance. that is referring to the mathematical representation of reactance, not the real life. Okay, real life reactance has a basis, it has a physical basis. Mathematically speaking, we refer it to as the imaginary reactance. Is that clear to everyone? I mean, is the distinction clear to everyone? Okay. If you read the words imaginary reactance, it is referring to the mathematical representation. Okay. With regards to the complex number math, because complex numbers have a real as well as an imaginary component. Which, by the way, in electrical engineering, the imaginary number is J, not I. I is used for current, so J is used for the imaginary number. So Z, complex impedance, is resistance plus Jx. Real resistance, imaginary reactance. So if you read a book, that's how they would refer to it, those quantities. Yes. Well, impedance is basically the sum of the resistance and reactance. So yes, it does. It does. In fact, if you look at any amplifier, audio equipment, if you look at any amplifier, if you look at any speaker, it will state in the specifications the impedance of that speaker. Speaker has a coil. Coil is nothing but an inductor. So it will state the impedance because the input coming into that coil is all AC. What I speak, the sounds that we make is captured by the microphone. And depending on the tone or the volume, of the sound signal, the electrical signal will have a different frequency. So different frequencies, meaning it's going to cause a different opposition in the speaker coil. And so it has reactance, it has impedance. Typical speakers are about 8 ohms or 6 ohms impedance. So if you look at the spec sheet of an amplifier, at the end of the manual, it'll state it can supply, let's say, 100 watts per channel or for 2 channels into an 8 ohm speaker impedance. That's where it comes from. Yes. So that's going to be the next point. But any other questions about the concept? Again, mathematically speaking, we'll look at all the problems and all of the derivations and everything. But I just wanted to give you a little bit brief overview of what reactance is before I move into the math. Okay, so again, reactance has a physical basis, impedance has a physical basis, but using math, we represent it using the imaginary number. So they are represented by the same symbol, and the unit for all three is ohms. So all of them are represented using the same symbol as for resistance, and the unit for all of them is the same, ohms. And because it's a complex, quantity, if you plot all three of those on the same chart, you get what is known as the impedance triangle. Impedance triangle, where the magnitude of the impedance and the phase angle describes the vector, and then the real and the imaginary portions describe the projection of that vector on the real and the imaginary axis. So resistance is on the real axis, reactance X is on the Y axis. Okay. Now, I said phasors are representation of the sources as a vector, and impedances are representations of the components as vectors, right? And I gave a brief explanation of what a reactance is. So what is the impedance of a resistor? If you've done the lab, you already know the answer, but just conceptually speaking, anyone? It's just the value of the resistor, right? So everybody who's at least taken the lab would know, but the concept that I just stated, right? Reactance arises from the fact that the electric and the magnetic field oppose any change in the input current or the input voltage. Since a resistor does not store energy, it does not have any reactance. Hence, the reactance is equal to 0. So it would be R plus J0, which would simply be R itself. Hence, there is no such thing as the impedance of a resistor. It is simply the resistor itself, and hence the resistor behaves exactly the same way it does for AC, the same it does for DC. Okay. So again, there's no such thing as ZR. I use ZR for explanation purposes. It's simply the resistor R. And then ZL, impedance of an inductor, would be the resistance of the inductor plus the reactance. But ideal inductors do not have any resistance. In the lab, you'd have used low quality inductors which had resistance, but ideal inductors, which is all we do in circuit analysis, theoretical analysis is ideal, meaning it is simply JXL. And XL is given by omega times L, product of omega times the inductor L. Omega is 2 pi F. So you can use either one of those. If the problem gives you omega in radians per second, you use omega L. If it gives you frequency in hertz, you use 2 pi FL. And you should be familiar with both, because depending on, the industry you work for, they could be using omega, they could be using frequency in hertz. You need to be familiar with both. Okay. So again, ideal inductors do not have any resistance. So ZL, impedance of a inductor, is simply J omega L or J 2 pi FL. For a capacitor, ZC is 0 minus J XC or minus J XC. XC is given by 1 over omega C, and that comes out to be 1 over 2 pi FC, frequency in hertz. Okay. 1 over J 2 pi FC. There is a reason it is minus. It is 1 over J 2 pi FC. So those are rectangular coordinates. If you translate into polar coordinates, it becomes omega L with an angle of plus 90. And for a capacitor, it's angle minus 90. And I'll explain why that is. But any questions before I get to that explanation? Again, these are all just equations. You can have them on your equation sheet, but you should know how to use them and apply them. Okay. All right. So remember, I talked about phase on Monday. Phase shift or phase difference between two or more waveforms. One waveform arrives at 0, 0 ahead of another waveform. We say it is leading the other waveform. Or if it's behind, we say it's lagging the other waveform. For a capacitor and for an inductor, the voltage and current are not in phase. For a resistor, they are in phase. For an inductor and capacitor, they are not in phase. Again, because it's energy transfer, there's a difference in phase of 90 degrees. So for an inductor, the voltage leads the current by 90 degrees. Okay, voltage leads the current by 90 degrees. And it's the exact opposite for a capacitor. Capacitor, the current leads the voltage by 90 degrees. Now, what that means is, if you're performing calculations ZL and you're getting a little bit ahead, on the next couple of slides, I will show and talk about how we can apply fundamental laws to circuit analysis problems for AC. So, you know what? Actually, let's go over to that slide and I'll come back to this point after that, because it'll make more sense after I do and show this. So, fundamental laws, Ohm's law, KVL, KCL, all the current laws, the voltage laws, superposition, mesh current analysis, node voltage analysis, everything still works exactly the same as it did for DC analysis, except the math now uses complex numbers. So Ohm's law is V equals IR. You perform complex math, you can replace I with Z and it becomes V equals IZ. If you use RMS values and not peak values, and we don't care about the phase, or we don't need the phase, then we can also use V equals I times X. It works exactly the same. So instead of doing V equals L di over dt, or C current IC equals C dV over dt, performing doing differentiation or integration or solving differential equations, we simply perform multiplication. Does that make sense? Right? Rather than solving differential equations, we perform a simple multiplication. And it's not like even like 30 years ago. You have programmable calculators now. You just enter the equation and it spits out a final value. So it's much, much, much easier now. 50, 60, 70 years ago, everybody solved this using manual methods, right? Now it's so much easier. So Ohm's law still applies, V equals IZ. So if you're trying to find the voltage across a resistor, you apply Ohm's law, V equals IR times R. If you're trying to find the voltage across a inductor or a capacitor, you apply Ohm's law, you find the current flowing through the inductor, find the impedance, perform a multiplication, and you're done. You don't have to solve any differential equations. And that is the beauty of using complex number math. It makes the math less complex. Does that statement make more sense now? Right? And so KVL, KCL, everything works. If you did lab 6, lab 7, you'd apply KVL. If you just look at the magnitude, which is the measured value, then the numbers don't make sense because you're not taking the phase angles into account. And that was the point of the phasor diagrams. The phasor diagrams take the phase angles into account. So KVL, just with the magnitude of the voltages, will not make sense. But KVL with the magnitudes as well as the phase angles will make sense. So if you wish to just go a little bit further, you can take the results of lab 6. You would have magnitude and you'd have phase for the inductor voltage, the capacitor voltage, and the resistor voltage, and the source. Apply KVL, meaning just sum up all three of those values, and you should get equal to 0. Which is actually a good way for you to practice, which is the next point that I want to make. Okay? But is this clear? You can still use all of these techniques, except the math is now using complex numbers. Any questions? Any questions from anyone? Okay, so this is the important point this is the point where I remind students or make a note that you need to be adept, skilled, or be an expert at using your own calculators to perform complex math or complex number math. Okay, my calculator is from the 90s, specifically 1992. Yeah, it's that old. That's when I started. So I cannot program equations in there. Okay, I have to solve it manually. I can do a transformation between polar and rectangular coordinates and then do the math manually after that. But I cannot perform complex number math equations directly. Right? If you have a newer calculator from nowadays, like TI-83, TI-84 Plus, Casio, can't remember, FX200 or something, they can all handle direct equations. You could plug in like some complex number multiplied by some complex number, subtracted, minus some complex number, and it would simply spit out a final value. I can't do that on my calculator. So again, you need to be an expert at your devices. There is a worksheet that is there on the website, again, from the beginning of the quarter. It's called complex math worksheet. Download that, practice, and then, until you become skilled at doing so. And again, this is not specific to electrical engineering. You can use it for any science or any scientific field or any engineering field. Many students would have taken classes with similar math. And if you've not, then sometime in the future, you might come across it. So VL is IL or Z, VL is I times Z. So Z, the impedance, similar to the resistance, is voltage divided by the current. Z is V over I. So ZL, impedance of an inductor, can be determined from the voltage for that inductor divided by the current for that inductor, VL over IL. Similarly here, VC over ZC. VC over IC. Now, if you're performing this math, what happens to the phase or the phase angles? Let's go here. We'll finish this and we'll come back to that later again. If you have two numbers, one of them in polar coordinate and the other one in rectangular coordinates, then it is easier, not impossible, but it's easier to perform addition and subtraction if both of them are in rectangular coordinates, and it's easier to perform multiplication and division if you have polar coordinates. Coordinates are the same thing. It's just you have a vector with length and phase angle. The projection of that vector on the x-axis gives you the real number, and the projection of that vector on the imaginary axis gives you the imaginary number. Okay? So it's just a different representation using different coordinates. That's all it is. So if you're trying to add, let's say A plus or minus JB, that's one number, and I was trying to add or subtract with another number in rectangular coordinates, C plus or minus JD, you would simply combine the real parts together and then combine the imaginary parts together. So you would add or subtract the real parts, and then you would add or subtract the imaginary parts. So this you can do manually. That's why, as I said, my calculator, I can transform a polar number, polar coordinates to rectangular coordinates and perform the addition or subtraction manually. If I was trying to perform multiplication, number, let's say A with a phase angle theta B, multiplied with B, not B, C with phase angle theta D. Magnitudes get multiplied, so it becomes A times C, and phase angles are summed up, theta B plus theta D. How many of you are familiar with this? No one? Okay. Some of it at least. A theta B divided by C in the phase angle theta D. Magnitudes get divided, A divided by C. Again, something I can perform on a simple calculator. And the phase angles are subtracted. Again, subtraction is something you can perform manually, or you can do it on a simple calculator. Okay, so now if we go back to the impedance equation, VL or IL, what do we see? For an inductor, the phase of that impedance, the phase angle of that impedance would be theta V minus theta I, phase for the voltage minus the phase for the current, which would be plus 90 because the voltage is ahead of the current. So the phase angle for an inductor is always pointing up. It's plus 90. Real and imaginary axis, it's a vector that rotates counterclockwise. Starting from 0, plus 90, plus 180, plus 270, and back to 360. And if it's VC over IC, it's theta V minus theta I again. But this time, the current for the current for the capacitor is ahead, meaning the voltage lags the current by 90 degrees. So it turns out to be minus 90 degrees. So inductor points straight up, capacitor points straight down, minus 90. For those of you who took the lab, if you remember, procedure number 2, where the phasor for the capacitor was pointing straight down. And that's the reason why. So the actual phase difference between the impedance of a capacitor and an inductor in a series circuit will always be 180, plus 90 and minus 90. So 180 degrees phase shift. Does that make sense? And this relationship is true for all inductors, for all capacitors, no matter their size, no matter the source, no matter the connections, because this is specific to each component. Meaning if there are multiple inductors and multiple capacitors in a circuit, if you take one single inductor, the phase difference between the voltage and the current for that inductor is separated by 90 degrees. Okay. The voltage for that inductor could be 78 degrees, but the current would always be 90 degrees behind. So it'd be minus 12. Does that make sense? Okay. This is specific only to that single component. Do not mix it up. You cannot take voltage from one inductor and measure it with respect to current for another inductor and say it does not add up to 90. Okay, this is specific to each individual component, not to any other. Yes. Impedance, yes, we will do that. Example 5. No, because we are representing voltages and currents also as phasors, as complex quantity. Remember, we're going to do, we can represent it. Oh, I see what you're saying. Have a phasor diagram which shows both voltages, currents, and impedances on the same. Then, yes, you can show it individually. Yes, yes. I will show it on the in example 5. Yeah, they will all be vectors, and you can represent it in the complex plane on the same phasor diagram. That was fundamental laws. Impedances. One final important slide is impedances add up the same way you add up resistors. Reactance is also the same. Impedance, resistance, and reactance are all kind of synonyms. I mean, obviously, impedance is the sum of resistance and reactance, but they have the same symbol, they have the same representation, they have the same units, everything is the same. So when we have a circuit and you have an inductor and a capacitor, doesn't matter how they are connected, we obviously can combine inductors together, we can combine capacitors together, but we cannot combine inductors and capacitors together. But if you represent their impedances, then you can combine the impedances together. ZEQ between the outer terminals would simply be ZL plus ZC because they're in series. Important distinction. Again, we are not combining the inductor and the capacitor. We are combining their impedances together, which we can do. Okay, we cannot combine L and C, but we can combine ZL and ZC. Whether they're connected in series or whether they're connected in parallel, they add up the same way that you add up resistors in series and parallel. Okay, so if it's parallel, it's Z is the reciprocal of the sum of all the reciprocals of the impedances, 1 over Z1 plus 1 over Z2, so on and so forth. We will see this in example 5. Okay, and you've already seen this in pre-lab 6 or 7. If you're taking the lab, you'll see this in 7. You'll see it in 7, lab 7. Yes. That's ideal inductors. Sorry, that's real life inductors. We don't take that into account here. These are all ideal. Everything on in 201, ideal components, ideal sources. If we see a 10 ohm resistor, we use 10 ohms. We do not measure it or use 9.98 or 10.01. 10 ohm resistor is 10 ohms. A 10 millihenry inductor is 10 millihenry. Resistance R is 0. Same thing for capacitors. Theoretical circuit analysis is always with ideal components. And one final thing is the terms admittance, conductance, and susceptance. Okay, they're all reciprocals of each of these terms that we just learned: impedance, resistance, and reactance. They are all reciprocals of each other. They are noted by Y, G, and B. Impedance Z is reciprocal. Sorry, admittance Y is the reciprocal of impedance. Conductance is reciprocal of R, susceptance of X. You will not see this in 201, not for non-E major class, okay? You've seen this in the lab. So impedance is impede. Admittance comes from admit, reciprocal. Resistance from resist. Conductance from conduct. Permits the flow, resists the flow, right? Reciprocals of each other. Reactance, of course, is from the reaction of the magnetic and the electric fields. And susceptance is the reciprocal of reactance. Susceptible, that's where it comes from. The unit for all three is ohms, right? Impedance, resistance, and reactance is ohms. And the reciprocals are named after the German physicist Siemens. I can't remember the first name. Carl Siemens or Joseph Siemens, I can't remember. But name after the German physicist Siemens. Conductance is used a lot in electrical engineering. But the way this was useful was because when you have to do manual calculations, it's easier, especially for a parallel circuit where we have to take reciprocals, right? We just saw here, you have to do this. Now, if you have to do this without a calculator, even with a calculator, this is going to be difficult to just program everything in there. You're programming a lot of reciprocals all at the same time. One long equation. So it is easier to work with Y, G, and B. If you already have reciprocals for your inductor, resistor, and capacitor, you can simply write G and BL and BC, and you simply sum it up. Total YEQ is simply G plus BL plus BC. Simple summation. And that's why it's easier to work with reciprocals. That's why we had these quantities. Okay. All right, we'll end class here. And I will pick up here again on Friday with the 5 examples. Homework 15 was due tonight. I moved it tomorrow night. But that homework is concept-based, short answer questions. Is completely based on the material we covered on Monday, not today. Okay. So several students have already started and even finished that homework. I would urge you to do the same. I'll be in my office. If you have any questions, reach out to me. Otherwise, I'll bid you a good day and I'll see you all on Friday. It should